Hey, Henry.
Hi, Michael.
Hey, it's great to have you here on the channel and just a moment on the podcast. It's going to be a lot of fun, isn't it?
Yes, thanks for having me.
Yeah, you bet. So yeah, let's kick it off and talk about some high energy physics and a bunch of packages and all sorts of cool stuff. There's a lot to cover, so I'm excited to get to it. Henry, welcome to Talk Python to me.
Thank you.
Yeah, it's great to have you here. I'm always fascinated with cutting edge physics, with maybe both ends of physics, right? I'm like really fascinated with astrophysics and the super large, and then also the very, very small. And we're going to probably tend a little bit towards the smaller high energy things this time around, but so much fun to talk about this stuff and how it intersects Python.
Yeah, some of the smallest things you can measure and some of the largest amounts of data you can get out.
Yeah. Yeah. The data story is actually really, really crazy. And we're going to talk a bit about that. But so neat, so much stuff. Like we used to think that, atoms were as small as things could get, right? Like I remember learning that in elementary school, like there are these things called atoms. They combine to form compounds and stuff. And that's as small as it gets. And yeah, not so much, right?
Yeah, and that was sort of what atom was supposed to mean.
Exactly, the smallest bit, but nope. But that name got used up, so there we are. All right, well, before we get into all that stuff, though, let's start with your story. How do you get into programming in Python?
Well, I started with a little bit of programming that my dad taught me. He was a physicist. And I remember it was C++ and sort of taught the way you would teach Java, all objects and classes.
Yeah.
Did just a little bit. And then when I started at college, then I wanted to take classes, and I took a couple classes again in C++. But I just really loved objects and classes, which unfortunately the courses didn't actually cover that much, but the book did. So I really got into that. And then for Python, actually, right when I started college, I started using this program called Blender, and it had a
Blender. I've heard of Blender. It's like 3D animation tool, like Maya or something like that, right?
Mm-hmm. Yes, but open source.
It's very
really
Python.
Really cool community.
Yeah, it's very Python friendly, right?
Yes, it has a built-in Python interpreter, and so I knew it had this built-in language called Python, so that made me really want to learn Python. And then when I went to an REU, a research experience for undergraduates at Northwestern University in Chicago. And when I was there, we had this cluster that we were working on. This was in solid state physics, material physics. Mm-hmm. And we would launch these simulations on the cluster. And so I started using Python, and I was able to write a program that would go out and it would create a bunch of threads, and it would watch all of the cluster, all the nodes in the cluster. And as soon as one became available, it would take it. So my simulation could just take the entire cluster. After a few hours, I would have everything. So at the end of that, everybody hated me and everybody wanted my scripts.
Exactly. They're like, this is horrible. I can't believe you did that to me, but I'll completely forgive you if you just give it to me and only to me, because I need that power. Yeah, that's fantastic. How neat. So, I think that is one of the cool things about Python, right? Is that it has this like quick prototyping approachability. That you're like, I'm just going to take over, a huge hardware, right? Like a huge cluster of servers, but it itself doesn't have to be like intense programming. It can be like this elegant little bit of code, right?
You can sort of do things that normally I think the programming gets in the way more, but Python tends to stay out. It looks more like pseudocode, so you can do more and learn more, and eventually you can go do it in C++ or something. But yeah,
absolutely.
Or
maybe not. Sometimes you do need to go do it in some other language, and sometimes you don't. I think the stuff at CERN and LHC has an interesting exchange between C++ and maybe some more Python and whatnot. So that'll be fun to talk about.
Yeah, we've been C++ originally, but Python is really showing up in a lot more places, and there's been a lot of movement in that direction. Yeah. And there've been some really interesting things that have come out. A lot of interesting things have come out of the LHC, computing wise as well as physics.
Awesome. Yeah, as a computing bit of infrastructure, there's a ton going on there. And as physics, it's kind of the center of the particle physics world, right? So it's got those two parallel things generating all sorts of cool stuff. I want to go back to just really quickly to, you talked about your dad teaching a little programming. If people are out there and they're the dad, they want to teach their kids a little bit of programming, I want to give a shout out to codecombat.com. Such a cool place. My daughter just yesterday was like, hey, Dad, I want to do a little Python. Remember that game that taught me programming? I'm like, yeah, sure. So she's like, she logged in and started playing, and you basically solve a dungeon interactively by writing Python. And it's such an approachable way, but it's not the like draggy droppy fake stuff. You write real Python, which I think is cool to introduce kids that way. So anyway, a shout out to them. I had them on the podcast before, but it's cool to see kids like taking to it in that way, right? Whereas you say it like, you could write a terminal app. They're like, I don't want to do that. But solve a dungeon, yeah, they could do that.
Yeah, I've actually played with a couple of those. They're actually really fun just to play with.
Yeah, they are, exactly. I did like 40 dungeons along with my daughter. It was very cool. Mm-hmm. How about now? What do you do now?
So I work in a lot of different areas, and I jump around a lot. So I do a mix of coding. I do some work on websites, because they just needed maintenance, and somehow I got volunteered, and some writing. So less coding than I would like, but I definitely do get to do it, which is fun.
Yeah, and this is at CERN or at your university, or where is this?
So now I'm at Princeton University, and I'm part of a sort of a local group of RSEs, Research Software Engineers. And I'm also part of the IRIS-HEP, which we'll talk about in a little bit. But that's sort of a very spread out group. A few of us are at CERN, a few are in some other places, a few in some Fermilab. And high-energy physicists are just used to working remote. The pandemic wasn't that big of a change for us. We were already doing all our meetings remote. We just eventually changed from video to Zoom, but other than that, it was
exactly. It was real similar for me as well. That's interesting. Fermilab, that's in Chicago, outside Chicago, right?
Yes.
Is that still going? I got the sense that was shutting down.
So they're big in neutrino physics. So they do a lot of neutrino things there, and then they're also very active just in the particle physics space. So you may be at Fermilab, but working on CERN data.
I see. Okay, interesting. Yeah, I got to tour that place a little bit, and it's a really neat place.
Oh, it is. CERN's a neat place too.
I would love to tour CERN, but it wasn't 20 minutes down the street from where I happened to be, so I didn't make it there. Sadly, I hope to get back there someday. All right. Well, let's talk about sort of the scikit-HEP side of things and how you got into maintaining all of these packages. So you found yourself in this place where you're working on tools that help other people build packages for the physicists and data scientists and so on, right? So where'd that all start?
So with maintenance itself, the first thing I started maintaining was a package called Plumbum back in 2015. And at that point, I was starting to submit some PRs, and the author came to me and said, I would like to have somebody do the releases. I need a release manager. I don't have enough time. Okay. And I said, sure, I'd be happy to do it. And it was exciting for me because it was the first package or like real package I got to join. And so I think on the page, I might even still have the original news item when it says welcome to me. But nice. So that was the first thing I started maintaining. And then I was working on a high-energy physics tool called GoofIt when I became a postdoc. And I worked on sort of really renovating that. It started out as a code written by physicists. And I worked on making it actually installable and packaged nicely, and worked with a student to add Python bindings to it, things like that. And as part of that, I wrote a C++ package, CLI 11. This is first package I actually wrote and then maintained. That's actually in C++. And it was written for GoofIt, but now it's a fairly, I think it's done pretty well on its own.
Nice. What's that one do?
What's that? Uses it.
Yeah, Microsoft Terminal uses it.
Mm-hmm.
Oh, nice. Yeah, I'm a big fan of
LVM.
Microsoft Terminal. I've for a while now kind of shied away from working on Windows because the terminal experience has been really crummy. You know, the cmd.exe command prompt style is just like, oh, why is it so painful? And people who work in that all day, they might not see this painful, but if you get to work in something like a Mac OS terminal, or even to not quite the same degree, but still in like a Linux one, then all of a sudden, yeah, it kind of gets there. So I'm kind of warming up to it again with Windows Terminal.
Yeah, the Xterm is one of the reasons I really moved to Mac, because I loved Xterm, and then Windows Terminal is amazing. Now it's a great team working on it, including the fact that they used my parser. But it's actually quite nice. The only problem I have in Windows 10 is it's really hard to get the thing to show up instead of CMD prompt.
Yeah,
but
I think
Windows
it's
11,
Windows 11, right?
The only one. Yeah,
I definitely think it's included now, which is great. So CLI 11, this is a C++ 11 command line parser, right? Like click or argparse or something like that, but for C++, right?
Yes, it was designed off of the Plumbum command line parser, because Plumbum is sort of a toolkit. It has several different things. I wish those things had been pulled out, because I think on their own they might have maybe even been popular on their own.
Right.
It has a really nice parser, but it was sort of designed off of that and off click. So it has some similarities to both of those.
Yeah, I think probably that's a challenge. I mean, we're going to get into scikit-HEP with a whole bunch of these different packages, but finding the right granularity of what is a self-contained unit that you want to share with people, or versus things like pulling out a command line parser rather than some other library, right? This is a careful balance.
It's a bit challenging. I think in Python there's a really strong emphasis to having the individual separate pieces and packages, especially in Python, partially because it has a really good packaging system, and that being able to take things, have just pieces, and being able to swap out one that you don't like is really, really nice. And that's one of the things we'll talk about the PyPI as well. And that's one of the things that they focus on, is small individual packages that each do a job versus like all in one.
Yeah.
Poetry type thing.
Yeah. Well, you'll have to do some checking or some fact checking, balancing, modernizing for me. I did professional C++ development for a couple of years, and I really enjoyed it until there were better options. And then I'm like, well, why am I still doing this? I'll go work on those. But one of the things that struck me as a big difference, to that world, is basically the number of libraries you use, the granularity of the libraries you use, the relative acceptance of things like pip, and the ease of using another library, right? If in C++, you've got the header and you've got the linked file and you've got the DLL, and there's like all sorts of stuff that can like get out of sync and go crazy and like make weird crashes. Your app just goes away, and that's not great. Is that still true? I feel like that difference is one of the things that allows for people to make these smaller composable pieces in Python.
I think that has a lot to do with it. What has happened in C++ is there's sort of a rise of a lot of header-only libraries. And these libraries are a lot easier to just drop into your project, because all you do is you put in the headers, and you don't have to deal with a lot of the original issues. So a lot of these small standalone libraries are header-only. One of the next things that I picked up as a maintainer was PyBind 11, and I've sort of been in that space, sort of between C++ and Python for quite a bit. I kind of like being in that area.
Yeah.
Just joining the two.
I get a sense from listening to the things that you've worked on previously and things like this, that you're interested in connecting and enabling, like piecing together, like, here's my script that's going to pull together the compute on this cluster, or here's this library that pulls together Python and C++ and so on.
Yes, making different things work together, and combining things like C++ and Python, or combining different packages in Python, and piecing together a solution. I think that's one of Python's strengths versus something like MATLAB. Spent quite a bit of time in MATLAB early on, and got to move a lot of stuff over to Python.
Right on. That's awesome.
It was really nice. We didn't have to have a license and things like that.
I know it's so expensive. And then you get what are they called? Toolkits, the add-on toolkits. And they're like, each toolkit is the price of, another $1,000 a year, $2,000 a year. It's ridiculous. So I know of CFFI, which is a way for Python and C to get clicked together in a simple way. How's PyBind 11 fit into that? This is seamless interoperability between C++ 11 and Python. How are they different?
So CFFI, I teach like a little short course where I can go through some of the different binding tools. And it usually ends with me saying PyBind 11 is my favorite. But
yeah, cool. Give us an overview of what the options are and stuff. Yeah,
is closer to C types. It's more of it's focused on C versus C++. And it's actually the one I've used the least. I was just helping, or just talking with the CFFI developer, but I've used it the least of those. But I think it basically parses your C headers and then sort of automates a lot of what you would have to manually do with C types. So you have to specify what symbol you want to call and what the arguments are and what the return type is. And if one of those things is wrong, you get a seg fault and that sort of thing. Whereas PyBind 11, this is about building modules, extension modules. So, and it's the interesting thing about this is that it's written in pure C++. The other tools out there, so Cython can do this. It's not what it was designed for, but it immediately became popular for doing this because Cython turned code, Python-like code is a new language, it transpiled it into C or C++. It had a toggle you could change, has a toggle you can change. And then when you're there, you can now call C or C++. But it's extremely verbose and you repeat yourself and you have to learn another language. It's this weird combined Python thing. And just thinking in Cython is difficult because you have to think about, well, am I in Python or am I in Cython that's going to be bound to Python, or am I in Cython that's just going straight to C++, or am I just in C++?
Yeah.
Or C, but I suppose
it's a lot of layers there. Yeah.
PyBind 11 is just C++, and it's basically, it's like the C API for Python, but a C++ API. So it's quite natural, and you don't have to learn a new language. It uses some fairly advanced C++, but that's it. You're learning something useful anyway.
Right. So do you do some sort of like template type thing and then say, I'm going to expose this class to Python or something like that, and then it figures out, does it write the Python code or what is it?
It's writing the
build like .so files, or what do you do here?
It compiles into the C API calls, and then that would compile into a .so.
Right.
And there's no separate step like Cython or Swig or these other tools, because it's just C++. You compile it like you do any other C++, but it's actually internally using the CPython API or PyPI's wrapper for it.
Yeah, well, that's really cool.
And the language looks a lot like Python, but the names are similar. You just do a def to define a function, and you give it the name, and then you just pass it the pointer to the underlying thing. It can figure out things like types and stuff like that for you. Give it a docstring if you want. Give the arguments names. Just you can make it as Pythonic as you want.
Yeah,
it's verbose, but it's not overly verbose.
Yeah, that's really neat.
Nice.
And for people who haven't used those kind of outputs, basically it's just import module name, whether it's a .py file or it's a
if you've used PyTorch, if you've used SciPy, if you've used any of those things, you've been importing some PyBind 11 code.
Okay. Yeah, awesome. All right. So let's talk a little bit about scikit-HEP. This is one of the projects, that it has a lot of these packages inside of it, and your library Cibuildwheel, excuse me, is one of the things that is used to maintain and build a lot of those packages, because I'm sure they have a lot of interesting and oddball dependencies, right? I mean, C++ is kind of standard, but there's probably others as well, right?
It is. So one thing that is kind of somewhat unique to HEP is that we are very heavily invested in C++. So it's usually either you're going to see Python or you're going to see some sort of C++ package of some sort. I mean, it could be, varies in size there, but it's mostly C++ or Python. We really haven't used other languages much for the past early 90s or so.
Is that inertia, or is that by choice? You know, why is that?
I think it's partially the community is a fairly cohesive community. We're really used to sort of working together. The experiments themselves are often, might be 1,000 or several thousand physicists working on a single experiment. And we have been fairly good about sort of meeting together and sort of deciding the direction that we want to go in, and then sort of sticking to that. So for C++, it was heavily root, which is a giant C++ framework, and it got everything in it. And that was C++, and that's what everybody used.
Right.
And
so root is the library. If I was going to write code that would run and interact with like the grid computing or the data access and all that kind of stuff at LHC, I would use this root library if I was doing that in C++, right?
Yes. And you might be using interpreted C++, which is something we invented.
Oh, okay. This is interesting. Is this something people can use?
Oh, yes. We actually, scient was the original interpreter, and then it got replaced by Cling, which is built on the LLVM. And I think recently it was merged to mainline LLVM as Clang REPL, I think it's called. It's sort of a lightweight version. But yeah, it's a C+ interpreter. You can actually get Zeus Cling, which I think Quantstack does, but they package it as well, I think, as Zeus Cling.
Okay. Yeah, very interesting.
It's not, C++ really wasn't designed for a notebook, though. It does work, but you can't rerun a cell often because of you can't redefine things. Python is just really natural in a notebook, and C++ is not.
Right. Yeah, especially if you change the type, you compile it as an int, and then you're like, that should be a string. Like, yeah, that's not going to be a string. It's compiled. Yeah, interesting. So it seems to me like the community at CERN has decided, look, we need some low-level stuff, and there's some crazy low-level things that happen over there. People can check out a video. Maybe I'll mention a little bit later. But for that use, they've sort of gravitated towards C. And then for the other aspects, it sounds like Python is what everyone agreed to. It's like, hey, we want to visualize this. We want to do some notebook stuff. We want to piece things together. Something like that, right?
It's certainly moving that way. They definitely have sort of agreed that Python should be a first-class language and join C++. That was decided a few years ago. And I think that's been a great step in the right direction, because what was happening, people were coming in with Python knowledge. They wanted to use Pandas. I mean, I came in that way as well. Pandas and Numba and all these tools were really, really nice. And we were basically just having to write them all ourselves in C++. And it has a data frame, but why not just use Python, which is what people know anyway.
Panda exists, and there's a ton of people already doing the work, maintaining it for us. Shouldn't have to recreate.
Root literally has a string class.
Yeah,
they have their own. Literally, it's everything. They do everything. So, sort of the idea, and this is sort of the idea behind scikit-HEP, was to build this collection of packages that would just fill in the missing pieces, the things that high-energy physicists were used to and needed. And some of them are general and were just gaps in the data science ecosystem, and some things are very specific to high-energy physics. So scikit-HEP actually sort of originated as a single package. It sort of looked like root read at first. And it was invented by someone called Eduardo Rodriguez, who was actually in my office at CERN. And we're office mates. And
cool.
But he did something, I think, really brilliant when he did this. And that is he created an organization called scikit-HEP around it. And then he went out and spoke with people and got some of the other Python packages that existed at the time to join scikit-HEP, moved them over, and started building sort of a collection of some of the most popular Python packages at the time. And I thought that was great. And I really wanted scikit-HEP to become a collection of tools, separate tools, and for the scikit-HEP package to just be sort of a meta package that just grabbed all the rest. And that's actually kind of where it is now.
Right. I can pip install scikit-HEP. Is that right?
You can, and mostly, other than a few little things that are still in there that never got pulled out, that will mostly just install our most popular, maybe 15 or so packages, 20, 15 of our most popular packages.
Yeah. So it probably doesn't really do anything other than say it depends on those packages or something like that, right? And then by virtue of installing it, it'll grab all of it. Yeah. Yep. Yeah, that's a really cool idea, and I like it. So maybe one of the things I thought would be fun is to go through some of the packages there to give people a sense of what's in here. Some of these are pretty particular, and I don't think would find broad use outside of CERN. For example, conda forge root. It sounds like that's about building root so I can install it as a dependency or something like that, right?
Yeah, building root is horrible, and you actually now can get it as part of a conda package, which is just way better than anything that was available for attaching to a specific version of Python, because it has to compile against a very specific version of Python. But that's what it does. So unless you want something in root, then that's very HEP specific.
Yeah,
some of the more general ones, probably our first. Briefly mention our very first package that I think was really popular among high-energy physicists that we actually produced was uproot, which was just a pure Python package, so you didn't have to install it, that read root files. So again, very specific for somebody who was in high-energy physics, but you could actually read a root file and get your data without installing root, and that was a game changer. And so now you can actually install root slightly easier, but normally it's a multi-hour compile, and it's gotten better, but it's still a bit of a beast to compile, especially for Python.
That does sound like a beast. Oh my gosh! And
now you can just read in your files. It's basically Jim Povarsky basically just taught Python to understand to decompile the root file structure, and actually can write right now too, but originally reading. But
so this is like if I want to do if I want to create a notebook and maybe visualize some of the data, but I don't really need access to anything else. I shouldn't depend on this beast of almost its own operating system type of thing.
Yeah,
right.
We were very close to being able to use all the data science tools in Python, pandas, things like that. For most data worked fine. You just had to get the data, and I mean, I've done this too, where I had one special install of Python and root together that I'd worked several hours on, and it sat somewhere, and I would convert data with it. I'd move it to HDF5, and then I would do all the rest of the analysis in Python that didn't have root, because then I could do.
And then there's Python libraries that read that HDF5 format, right?
Mm-hmm. Yeah.
Right. Okay.
So the first package we had that was really popular on its own was awkward array.
Yeah,
and
awkward array
was originally
heard about this one. Yeah,
yeah, that was originally part of uproot, sort of grew out of uproot. But when you're reading root files, you end up with these jagged arrays. So that's an array that is not rectangular. So at least one dimension is jagged. It depends on the data, and this shows up in all sorts of places, and not just particle collisions. Or obviously shows up lots of places in particle collisions, like how many hits got triggered in the detector. That's a variable length list. How many tracks are in an event? That's a variable length list. And it can be a variable length list of structured data. And to store that compactly, the same way you'd use NumPy was one thing, but you arrow, and there's some other things that do this. But awkward array also gives you NumPy-like indexing and data manipulation. And that was the sort of the breakthrough thing here. It's like NumPy. The original one was built on top of NumPy. The new one actually has some PyBind 11 compiled bits and pieces, but it makes working with that really well. In fact, Jim Povarsky has now got a grant to expand this to, I don't remember the number of different disciplines that he's working with, but lots of different areas, genomics and things like that have use cases, and he's adding things like complex numbers and things that weren't originally needed by high-energy physicists, but make it widely
almost
useful.
an evangelism, like dev evangelism type of role, right? Go talk to the other groups and say, hey, we think you should be using this. What is it missing for you to really love it? Something like that, right?
Mm-hmm.
How interesting.
Yeah,
So
fairly large scale.
yeah. So looking at the awkward array page here, says for a similar problem 2 million times larger than this example given above, which one above is not totally simple. So that's pretty crazy. It says awkward array, the one-liner takes 4.6 seconds to run and uses 2 gigs of memory. The equivalent Python list and dictionaries takes over 2 minutes and uses 10 times as much memory, 22 gigs. So yeah, that's a pretty appealing value proposition there.
Yeah, and it supports Numba. Jim has been works very closely with the Numba teams and really is one of the experts on the Numba internals. So it has full Numba support now, and he's working on adding Dask. He's working with Anaconda on this grant, and then working with adding GPU support.
Very cool. Maybe not everyone out there knows what Numba is. Maybe give us a quick elevator pitch on Numba. I hear it makes Python code fast, right?
Yeah, it's a just-in-time compiler, and it takes Python. It actually takes the bytecode, and then it basically takes that back to something, or it parses the bytecode and turns it into LLVM. So it works a lot like Julia, except instead of a new language, it's actually reading Python bytecode, which is challenging because the Python bytecode is not something that stays static or is supposed to be a public detail.
It's not. Yeah, there's no public promises about consistency of bytecode across versions, because they play with that all the time to try to speed up things, and they add bytecodes and they try to do little optimizations. And
so every Python release breaks Numba, so they just know the next Python release will not support Numba, and it usually takes a month or 2.
Okay.
But
all right. So go ahead.
It's very impressive though. It's the speed up. So you do get full sort of C-type speed ups for something that looks just like Python. It compiles really fast for a small problem, and it's as fast as anything else you can do. I've tried lots of these various programming problems, and you just about can't beat Numba. It actually knows what your architecture is since it's just-in-time compiling. So you have to
which is an advantage over, say, like C, right? It can look exactly at what your platform is and your machine architecture and say, we're going to target, I see your CPU supports this special vectorized thing or whatever, and it's going to build that in, right?
Yeah. And then what sort of Jim does with Awkward, and we've done with some other things with Vector does this too. You can control what Python turns into, what LLVM constructs any Python turns into, because you can control that compile phase. That's incredibly powerful, because you can say, and it doesn't have to be the same thing, but obviously you want it to behave the same way. But you can say, if you see this structure, this is what it turns into in LLVM machine code, which then gets compiled, or machine language, which then gets compiled into your native machine language.
Interesting. So if you have like a certain data structure that can be well represented or gets packed up in a certain way to be super efficient, you can control that.
Yeah, you can say that, well, this operation on this data structure, this is what it should do, and then that turns into LLVM, and maybe it can get vectorized or things like that for you.
Yeah. Oh, that's super neat. Another package in the list that I got to talk about, because just the name and the graphic is fantastic, is a ghast. What is a ghast? It's got like this, the Scream. I forgot who was the artist of that, but the Scream sort of look as part of the logo is good.
Yeah, about half of the logos come from Jim, and I did about half. He did about half, and then a few other around are from the individual package authors. A ghast was, so this is sort of part of the histogramming area, which is where sort of the area I work in, scikit-HEP. But Jim actually wrote a ghast, and the idea was that it would convert between histogram representations. I think it came up because Jim got tired of writing histogram libraries. I think he's written at least 5. And,
one of the things I got by the sense of by looking through all the scikit-HEP stuff, there's a lot of histogram stuff happening over there.
Yeah, so histograms is sort of the area that I was in, and it ended up coming in several pieces. But I think one of the important things was actually, and I think Agast may not really matter, may get archived at some point, because instead of sort of translating between different representations of histograms in memory, what you can do is define a static typing protocol, and it can be checked by MyPy, that describes what a object needs to be called a histogram. And so I've defined that as a package called UHI, Universal Histogram Interface. And anything that implements UHI, and it can be fully checked by MyPy, will then be able to take any object from any library that implements UHI. And so all the libraries we have that produce histograms, so uproot, when it reads a root histogram, or hist and boost histogram, when they produce histograms, they don't need to depend on each other. They don't even depend on UHI. That's just a static dependency for MyPy time. And then they can be plotted in MPL-HEP, or they can be printed to the terminal with histoprint, and there's no dependencies there. One doesn't need the other.
Yeah.
And that's sort of making Agast somewhat unneeded, because now it really doesn't matter. You don't have to convert between two, because they both just work.
They work on the same underlying structure, basically, right?
They work through the same interface.
Right. Yeah. So Agast is a way to work with different histogramming libraries that kind of is the intermediary of that. It's like an abstraction layer on that. Okay. What are some other ones? Yeah. What are some other ones we should kind of give a shout out to? We talked about GoofIt, which is there.
That's an affiliated package. It's not part of scikit-HEP, but it has. So we developed this idea of an affiliated package, which are things that didn't need to be moved in, but had at least one scikit-HEP developer working with them. Or at least that's my definition. I was never able to actually get the rest to agree to exactly that definition, but that's that's my working definition. And so that's why PyBind 11 gets listed there. It's a affiliated package, because we share a developer, me, with the PyBind 11 library, and we sort of have a say in that and how that is developed. And most importantly, if we have somebody come into scikit-HEP, we want them to use PyBind 11 over the other tools, because that one we have a lot of experience with.
Very cool.
So
another one I thought was interesting is HEP units. So this idea of representing units, like, the standard units, they're not enough for us. We have our own kind of things, like molarity and stuff, but also luminosity and other stuff, right?
Yeah, different experiments can differ a bit. So there's a sort of a standard that got built up for units, and so this just sort of puts that together and has the unit that we've sort of decided on, this should be the standard unit. That's 1, and the rest are different scalars. So it's a very tiny little library. It was the first one to be fully statically typed because it was tiny.
That's easy to do.
It's like, because MyPy infers constants, there was like 2 functions or something, and then it was done.
Yeah. Probably a lot of floats.
So, but and that's sort of what it is. So you can use that and the idea is that the rest of the libraries will adhere to that system of units. So then if you use this and then use that the values it gives you, then you can have a nice human readable units and be sure of your units.
Yeah, that's really neat. Have you heard of Pint? Are you familiar with this one?
I love Pint.
Oh gosh,
but Pint actually takes the types through, and I use Pint some, but it actually gives you a quantity out, or a NumPy quantity, whereas the HEP unit just stays out of the way, and it's a way to be more clear in your code, but it's not enforced. Pint is enforced, which I like enforcing, but it's also can slow down. You can't, these are not actual real numbers anymore. So you pay.
Yeah. So it's going to add a ton of overhead, right? But Pint's interesting because you can do things like 3 times meter plus 4 times centimeter, and you end up with 3.04 meters.
Yeah, things those like are actually real quantities. They're actually a different object, which is the good thing about it, but it's also the reason that then it's not going to talk to, say, a C library that expects a regular number or something as well.
Sure. Okay. Maybe 1 or 2 more, and then we'll probably be out of time for these. What else should people maybe pay attention to that they could generally find useful over here?
I can mention vector. It's a little bit newer, but it's certainly for general physics. I think it's useful because it's a library for 2D, 3D, and relativistic vectors. And there aren't really, I mean, it's a very common sort of learning example you see, but there aren't really very many libraries that do this, that actually have, if you want to take the magnitude of a vector in 3D space, there just isn't a nice library for that. So we wrote vector to do that. And vector is supported by Awkward. It has an Awkward backend. It has a Numba backend, NumPy backend, and then plain object backend. And eventually we might work on more. And it even has a Numba Awkward. So you can use a vector inside an Awkward array, inside a Numba jet compiled loop, and still take magnitudes and do stuff like that.
Oh, that's really cool. That integration there. Yeah.
Vectors. Because we have a lot of those in physics.
Sure. And you can do things like ask if one vector is close to another vector and things like that, even in different, it looks like one in polar coordinates and one in, a Cartesian or something like that.
It has different unit systems, and it can actually, it actually stores the vector in that. So you don't waste memory or something if that's the representation you have. That was a feature from Root that we wanted to make sure we got. And it also has sort of the idea of momentums too and stuff for the relativistic stuff.
Yeah.
End up with a lot of that.
So,
and then,
yeah, go ahead.
And then maybe just mention since we mentioned the histogramming stuff, and that's the area, that's the ones that I really work on. The ones I specifically work on that are general purpose. Boost histogram is a wrapper for the C++ Boost histogram library.
Okay.
Boost is the sort of the big C++ library, just one step below the standard library. And right at the time I was starting at Princeton, I met the author of Boost histogram, who's from physics. And he was in the process, I believe, of getting this accepted into Boost. And it got accepted after that. But one of the things that he decided to do was pull out his initial Python bindings that were written in Boost Python, which is actually very similar to PyBind 11, but requires Boost instead of not requiring anything. But design is intentionally very similar. And so I proposed I would work on Boost histogram and write the Python bindings for it inside scikit-HEP. And that would be sort of the main project I started on when I started at Princeton. And that's what I did. Boost histogram is a extremely powerful histogramming library. So it's a histogram as an object rather than like in NumPy, there's a histogram function and you give it an array and then it spits a tuple of arrays back out at you that you are now, you now have to manage these. They don't have any special meaning. Whereas Boost histograms really are much more natural as an object, just like a data frame is more natural as an object, where you tie that information together. A histogram's really natural that way, where you still have the information about what the data actually was on the axes. If you have labels, you want to keep those attached to that, right, that data. And you may need to fill again, which is one of the main things that hydrophysicists really wanted, because we tend to fill histograms and then keep filling them or rebinning them or doing operations on them. And you can do all those very naturally. And Boost histogram is the C++ wrapper in PyBind 11. And I actually got involved in Cibuildwheel because of Boost histogram, because one of the things I wanted is make sure it worked everywhere, and it obviously requires C++, so it requires compilation.
Yeah.
And then Hist is a nice wrapper on top of that just makes it a lot more friendly to use, because the original Boost histogram author wants to keep this, Hans Stebinski, wants to keep this quite pure and clean. So Hist is more natural, and even if you're not in HEP, I think that's still the more natural one to use.
Yeah, and those right. There's a lot of people who use histograms across all sorts of disciplines, so that would definitely be one of those that is generally useful. All right, so I think that brings us to Cibuildwheel. Let's talk a bit about that, and I mean, maybe the place to start here is what are wheels, right? The first sentence describing it is Python wheels are great. Building them across Mac, Linux, Windows, and other multiple versions of Python, not so much. So
no description of what a wheel is.
Yeah, exactly. Well, wheels are good. There's times when there are no wheels and things install slower. They might not install at all. It's generally a bad thing if you don't have a wheel, but they're not easy to make, right? So tell us, what is a wheel, and then let's talk about why maybe building them across all these platforms and this cross product along with like versions of Python and whatnot is a mess.
Yeah, so when you distribute Python, you have several options. The most common one, and most packages have at least an sdist, which is just basically a tarball of the source.
Right. When you pip install it, it basically
maybe, or missing some things or adding some things, but
right. It
otherwise
basically
it's
unzips. Yeah, it unzips your source and puts it somewhere Python will find it, and then that's that.
Yeah, so it runs your build system. So setup tools traditionally, that's become a lot more powerful recently, but it has to run the build system to figure out what do you do with it. This is just a bunch of files, and then it puts it together in a particular structure in your on your computer. And so a wheel was a package that was already everything was already in place. So it's already in a particular structure. It knows the structure, and all Python has to do for a pure Python wheel, one that does not have any binary pieces in it, it just grabs the contents inside and dumps them following a specific set of rules into places into your site packages. Right. So then you now have something installed. There's no setup.py in your wheel. There's no pyproject.toml. There's those sorts of things are not in the wheel. The wheel's already there. It can't run arbitrary code.
Yeah, exactly. That was one of the points I was going to make. Is one of the things that can be scary about installing packages is just by virtue of installing them, you're running arbitrary code, because often that is execute, Python space setup py space, install or something like that. And like whatever that thing does, that's what happens when you pip install, right? But not with wheels, as you said, it comes down in a binary blob and just like, boom, here it is. Obviously the thinking is, we have this package delivered to 1 million computers. Why do we need to have every million computer run all the steps? Why don't we just run it once and then go here? And then also that saves you a ton of time, right? Like I just installed MicroWhiskey, and it took, I don't know, 30 seconds, 45 seconds to install because it didn't have a wheel. So it sat there and it just grinded away compiling it,
Yeah, so there's two possibilities. A pure Python package, a wheel is still superior because of the not running arbitrary code. Pip will actually go ahead and compile all your PYC files. So it goes ahead and makes the bytecode for all those. If it's a wheel, if it's a tarball, it doesn't do that. If it doesn't pass through the wheel stage anyway. And then every time you open the file, then it's going to have the first time it's going to have to make that bytecode. So it'll be a little slower the first time you open it. So there's a variety of reasons. I think it's pythonwheels.com, something like that, that describes why you should use wheels. Maybe that's not it, but I think it is. Yes, Python wheels. So they have like a list of advantages there. But
yeah, they also have a little like checklist. It says, how are we doing for the top 360 packages? And apparently 342 of them have wheels, and it shows you for your popular packages which ones like Click does, but Future doesn't, for example, and so on. So
yeah, Future's been there for a long time, and but yeah, so wheels are really good, and they actually replaced an older mechanism that was trying to do something somewhat similar called eggs, but I avoid talking about those. I don't really understand.
let it live in the past. Let it live in the past.
But wheels also are a great way if you have compile that happens. So if you compile some code as part of your build, then that of course is much slower. If you have the
like my MicroWhiskey example, it's like it was doing GCC
and
or
if you don't have a compiler, it won't even work.
Right, exactly.
Right? So you have to have some setup, at least a little setup. You have to have a compiler setup at the very minimum.
How many Windows users have seen cannot find vcvars.bat? Right.
You're like, what is this? You have to be in the environment, or you have to have the right script sourced. Yes.
Yeah.
So wheels also can contain binary components like .sos and things, and they have a tag as part of their name. They have a very special naming scheme for wheels. And the tag is stored in the wheel too. And they can tell you what Python version they're good for, what platform they are supported on. They have a build number, and then they have the Python's actually in two pieces. There's the ABI and the interface.
Mm-hmm.
Python.
Yeah, you can see there's some huge long name that with a bunch of underscores separating it, and basically,
yes.
It's when you try to pip install it. Sorry, go ahead.
It's also one of the reasons that names are normalized. There's no difference between a dash and an underscore. It's because that special wheel name has dashes in it. So the package name at that point in the file name has to be underscores.
Interesting. Yeah. Okay. Yeah. And so basically, when you pip install, it says it builds up that name and says, "Do you have this as a binary? Give it to me," right? Something like this.
Mm-hmm. Yeah, it knows how to pick out it looks for the right one. If it finds a binary, it'll just download it, depending slightly on the system and how new your pip is.
Right. And this is one of the main innovations, ideas, or philosophies behind Conda and Anaconda, right? Is like, let's just take that and make sure that we build all of these things in a really clear way, and then sort of package up the testing and compilation and distributing all that together, right?
Yes, this is very similar to this came, I'm pretty sure it came after Conda. I think they were still in eggs when Conda was invented. And then sort of building up wheels was challenging. Building a wheel was challenging. That's Cibuildwheel has really changed that. If you want a pure Python, it's really easy. Today you should be using the build tool, which I'm a maintainer of that as well. But build just builds an sdist for you, or it builds a wheel.
And so you could say something like Python setup py bdist or something like that, and then boom, out comes your wheel.
I shouldn't be doing that anymore. Please don't. But that is how you
how would I do it? Tell me the right way.
The best way. Well, you could do Python or pip install build, and then Python -m build, and that will build both an sdist and a wheel, and it'll build the wheel from the sdist. If you use pipx, which I would recommend, then you can just say pipx run build, and you don't have to do anything. That'll download build into a virtual environment for you. It'll do it, and then it'll throw away the virtual environment after a week.
Interesting. Okay. So we could just use the build. We should be using the build.
You should be using the build tool. For an sdist, there's a big benefit to this, and that is it will use your PyProject.toml, and if you say you require NumPy, then it will go, like you're using the NumPy headers, the C headers. Then it will go and it will, when it's building sdist, it will make a PEP 517 virtual environment. It'll install NumPy, anything that's in your requires in your PyProject.toml, and then it will run the setup.py inside that environment. So you can now import NumPy directly in there. And it'll work even when you're building an sdist. If you do Python sdist or Python setup.py stuff, it can't do that because you're literally running Python, giving it setup.py, import NumPy, now it's broken.
Right. Okay.
Nothing triggers that that call to the PyProject.toml to see what you need. For a wheel, the best way to do it is with pip, or the original way to do it was with pip wheel. Because pip has to be able to build wheels in order to install things. That got added to pip before build existed. But now the best way to do it would be with build wheel. And it's doing the right thing. It's actually trying to build the wheel you want, whereas pip wheel is actually just building a wheelhouse. So if you depend on NumPy and NumPy doesn't have wheels, which they did better with Python 3.10, so I'm not going to complain about NumPy for Python 3.10, but for 3.9, they didn't have wheels for a while. So it'll build the wheels there, and it'll build your wheels, and it'll dump them all in the wheelhouse, whatever the output is. So he'll be building NumPy wheels, which you definitely don't want to try to upload.
Yeah, definitely not. All right, well, that's really cool, and I definitely learned something. I will start using build instead of doing it the other way.
Yeah. You can now delete your setup.py too.
Yeah, that's the big thing, right? So you don't have to run that kind of stuff, right?
Yeah, they're trying to move away from any commands to setup.py because you don't even need one anymore, and you can't control that environment. It's very much an internal detail.
Yeah. So like wrapping up this segment of the conversation, we want a wheel because that's best. It installs without requiring the compiler tools on our system. It installs faster. It's built just for our platform. The challenge is when you become a maintainer, you got to solve this matrix of different Python versions that are supported and different platforms. Like, for example, there's macOS Intel, there's macOS M1, Apple Silicon, there's multiple versions of Windows, there's different versions of Linux, right? Like ARM Linux versus AMD 64 Linux.
And now Musil Linux versus the other Linux varieties. Yeah, so one of the challenges with the wheel is making it distributable. So if you just go out and you build a wheel and then you try to give it to someone else, it may not work. Certainly on Linux, if you try to, pretty much if you do that it just won't work because the systems are going to be different. On Mac OS, it'll only work on the version you compiled it on and not anything older. And you'll even see people trying to compile on Mac OS 10.14 because they want their wheels to work as in many places as you want.
Let's find the oldest,
one,
jankiest.
And,
well, exactly. Let's find the jankiest. Like I've got a Mac Mini from 2009. We're building on that thing because it will work for most people, right?
I think that's how they actually build the official Python binaries.
Interesting.
I'm not sure.
Well, but then Apple went in like last year around this time, they threw a big spanner in the works and said, you know what, we're going to completely switch to ARM and our own silicon, and you got to compile for something different now.
Yeah, and cross-compiling has always been a challenge. Yeah, and then Windows is actually the easiest of all of them. You're most likely on Windows to be able to compile something that you can give to someone else. But
yeah, that's true. That is one of the things that Microsoft's been really pretty good at is backwards compatibility. It holds them back in other ways, but yeah, typically you can run an app from 20 years ago and it'll still run. Yeah,
and there are a few caveats, but not many, at least compared to the other systems. Apple's really good, but you do have to understand how to you do have to set your minimum version, and you have to get a Python that had that minimum version set when it was compiled. But if you do that, it works really well. So what I actually started with in scikit-HEP, I was building Boost Histogram, which needed to be able to run anywhere. That was something I absolutely wanted. It had to be pip install Boost Histogram, and it just worked no matter what. And also we had several other compiled packages at the time. Several we had inherited. And iMenu was compiled, and that was quite popular. We had a couple of specific ones. And we had a couple more that ended up becoming interested in that. In fact, during this sort of period is when Awkward started compiling pieces. And so what I started with was building my own system to do this. It was called Azure Wheel Helpers, which was, as you can guess by the name, Azure was basically a set of Azure DevOps scripts. It was right after Azure had come out. Mm-hmm. And I wrote a series of blog posts on this and described the exact process and sort of the things I found out about how you build a compatible wheel. On Mac OS, you have to make sure you get the most compatible CPython from python.org itself. You can't use brew or something like that because those are going to be compiled for whatever system they were targeting. And on Linux, you have to run the mini Linux system, and you should run audit wheel. And actually, on Mac, you should run develop wheel. I might be getting it. I think it's develop wheel. So there's this series of things that you have to do. And I started maintaining this multi-hundred line set of scripts to do this. And I was also being limited by Azure at the time. They didn't have all the templates and stuff they have now. So everything had to be managed through Git subtree because it couldn't be a separate repository. And then when Jim started working on Awkward, he went and just rewrote the whole thing because he wanted it to look simpler for him, and took a couple things out that were needed and suddenly made it two separate things. Now I had to help maintain that. So when Python 3.8 or whatever it was came out, now I had a completely different set of changes I had to make for that one. And it was really just not working out. It was not very easy to maintain. And I was watching Cibuildwheel, and it was this package. It was a Python package that would do this, and it didn't matter what CI system you were on because it was written in Python, and it could follow nice sort of Python principles for good package design. It had unit tests and all that sort of stuff. So it looked really good. There were a couple things that was missing. I came in, I made PRs for the things that I'd come up with that it didn't have, and they got accepted. And there was a shared maintainer between PyBind 11 and Cibuildwheel as well. I think that's one of the reasons that I sort of had heard about it and was really watching it. And I finally decided just to make the switch. And I did, at some point a little later, I actually became a maintainer of Cibuildwheel. But I think I started doing the switch before. It made it really easy once I was a maintainer to say, oh, this is a package we have some control over. It's okay. Let's just
this is a safe place to depend upon this because we have a say.
Yeah. It just took out all of that maintenance, and now Dependabot does all the maintenance for us. It does the pin, moves forward a pin on Cibuildwheel, and that's it.
Nice. So if I want to accomplish, if I'm a package developer owner and I want to share that package with everybody, we've already determined we would ideally want to have a wheel, but getting that wheel is hard. So Cibuildwheel will let you integrate it, as the name indicates, into your continuous integration. And one of those steps of CI could be build the wheel, right?
So it reduces it down to pretty much that there's a step in your CI that says, run Cibuildwheel, and then Cibuildwheel is designed to really integrate nicely with the build matrix. So you could, for a fairly simple package or for many packages, you can really just do Mac, Windows, and Linux. You have the same job. Like in GitHub Actions, it's easy to do the same job. And then call Cibuildwheel. And that's about it. It just goes through all the different versions of Python that are supported. It just goes through and makes a wheel for each. And in fact, it even has one feature that was really nice that I'd always struggled with a bit. It has testing. So if you give it a test command, it will even take your package. It will install it in a new environment that's not, in a different directory that's not related to your build at all, and make sure it works and passes whatever test you give it. And
we'll do that across the platforms. We'll do like a Mac OS test and a Windows test.
Yeah, for each. So Cibuildwheel really just sees the platform it's sitting on because it's inside the build matrix, and so it's run for each. And it does for each one. It will run that test. And the simplest test is just echo, and that will just make sure it installs, because it won't try to install your wheel unless there's something in that test command. Even that's useful sometimes.
Yeah, sure.
So it's broken sometimes because of Numba not supporting one of those things in that matrix.
Yeah, it can't install the dependency, so that step fails or something. So it says it currently supports GitHub Actions, Azure Pipelines, which I don't know how long those are going to be two separate things. Maybe they'll always be separate, but Microsoft owning GitHub, I feel like they're saying do stuff in Azure Pipelines, and then they're kind of moving. I think they're similar.
The runners are the same. They actually have the same environments.
Okay.
So I think they'll exist just as two different interfaces probably. And Azure is not so tied to GitHub, and it has more of an enterprise type.
Yeah, for sure.
Focus,
definitely that's a different
GitHub
focus.
was just a rewrite, and a better rewrite in most cases of it. They got to learn.
Yeah, I think GitHub Actions came second. All right, so then Travis CI, AppBear, Circle CI, and GitLab CI. At least all of those, right?
At least those are the ones we test on. And then it runs locally. There are some limitations to running it locally. If you target Linux, and you can any system that has Docker can target Linux. You can just ask to build Linux wheels, and you can actually run it from like my Mac or from Windows. I assume from a Windows machine. I haven't tried Windows with Docker. And Windows, it does install to a standard location, C:\/Cibuildwheel, but other than that, it's safe to run it there. And Mac OS, it will install to your Mac OS system. It's installed system versions of Python. So that's something we haven't solved yet. We might be able to someday. So it's not a good idea unless you really are okay with installing every version of Python that ever existed into your
system. Maybe get a VM of your Mac.
The Python.org Python, but
yeah. It's somewhat safe. If you're on Windows, you could use Windows subsystem for Linux, WSL, as well, in addition to Docker, I suspect.
Well,
although I haven't tried that.
mini Linux has to run. I'm sure, as long as you can launch Docker. The thing that you have to be able to do is launch Docker, because you have to use the mini Linux Docker images, or you should use that or a derivative of that. There's lots of rules to exactly what can be in the environment and things like that. And PyPI maintains that. One thing that also helps is that we have the main mini Linux maintainer is also a Cibuildwheel maintainer. So it's one reason that those things tend that
they fit well together.
Features tend to match and come out at the same time, like MusaLinux, which is a big thing recently. It's not actually in a released version of Cibuildwheel yet.
What is MusaLinux?
So a normal Linux is based on glibc, and that's actually what controls. It's one of two things that controls mini Linux. So can you download the binary wheel, or do you have to build? If you have an old version of pip, that won't. They had to teach pip about each version of mini Linux. And that was a mess, so they eventually switched to a standard numbering system that is your glibc number. And now pip doesn't. And the current pip will be able to install a future mini Linux as long as your system supports it. But that was a big problem. So pip 9 can only install mini Linux 1. It can't install mini Linux 10, even if your glibc is fine for it. So the other thing is the glibc version, and mini Linux 1 was based on CentOS 5, Red Hat 5. Mini Linux 2010 was CentOS 6. Mini Linux 2014 was CentOS 7, and then now they switched to Debian because of CentOS sort of switching to the stream model. So Mini Linux 2.14 or 2.24 is glibc 2.24, and that's Debian 8 or something like that.
Okay, I see.
And so, but that's glibc based. There are distributions that are not glibc based, most notably Alpine. So if you ever used Alpine, it's this tiny little Docker image. It's a really fun distribution to use if you're on Docker. But it actually sounds fun to install, but I've never tried it without Docker. But it's these 5 megabyte Docker wheels, or Docker. I guess Docker doesn't do wheels. Docker images.
Docker images, yeah.
But that doesn't use glibc. That uses Musil. And so MusaLinux will run on Alpine.
Okay, got it. So if you're building for the platform Alpine and similar ones, right?
Mm-hmm. Mm-hmm. Yeah, so
anything cool.
built off Musil.
Yeah, and you said I can run this locally as well. I know I would use it in CI because I've got that matrix of all the versions of CPython and PyPI, PyPI, and then all the platforms that I want to check as many of those boxes as possible to put wheels in it, right?
Mm-hmm.
Suppose I'm on my Mac and I want to make use of this to fill in, maybe do some testing, at least on some of these columns. Like, how do I do that? What's the benefit there?
Well, I can tell you a case where it happened. So we were shipping CMake, and the scikit-build organization ran out of Travis credits, and they were being built. We hadn't switched them over to being emulated builds on GitHub Actions yet, and it just ran out. We couldn't build them, and one of them had been missed. And we also weren't waiting to upload, so we had uploaded everything, but we had one set, or maybe it was all of the emulated builds. I think it was one set of the emulated builds. It didn't work, and so we wanted to go ahead and upload those missing wheels. And I tried, but I couldn't actually get emulation, the Docker QEMU emulation. I couldn't get that working on my Mac. So the mini Linux maintainer used his Linux machine, and he had QEMU emulation on it, and he built the emulated images. It took a few hours, but he just built them locally and then uploaded them.
Okay.
So
yeah, very nice.
Missing wheels.
So if I'm maintaining a package, I got some package I'm putting on PyPI and I want to test it, does it make sense to do it locally, or does it just make sense to put it on some CI system?
For Cibuildwheel, usually I do some local testing, but I'm also developing Cibuildwheel. But usually it's probably fine to do this in your CI, and usually don't want to run the full thing every time. Usually you have your regular unit tests, because Cibuildwheel is going to be a lot slower because it's going through and it's making each set of wheels and launching Docker images and things like that. And it's installing Python each time for macOS and Windows. So usually, unless if you have a fairly quick build, I've seen some people just run Cibuildwheel as part of their test suite, but usually you just run it, say, right before a release. Maybe I usually do it once before the release and then on the release.
Right, exactly. Okay, that makes sense because it's a pretty heavyweight type of operation.
Yeah.
So when I look at all these different platforms, I see macOS Intel, macOS Apple Silicon, different bitnesses of Windows, and then I think about CI systems. What CI systems can I use that support all these things? Like, does GitHub Actions support both versions of macOS, for example, plus Windows?
GitHub Actions is by far our most popular platform. It switched very quickly. It used to be Travis. Travis was a challenge because they didn't do Windows they still don't do Windows very well. And it's a challenge for us because we actually can't run our macOS tests on them anymore, because once we joined the PyPI, the billing became an issue. And so we basically just lost macOS running for it. But Circle, I think, Azure and GitHub Actions, I think they do all three. And you can always split things up. I do Travis for the Linux and then AppFair for Windows. You can do it that way. One of the big things that I helped develop for Cibuildwheel was the pyproject.toml or any toml configuration, but usually that one, configuration for Cibuildwheel. So that way you can get your Cibuildwheel configuration out of your YAML files. That way it works locally, which is one of the things I was after, but also you can just do it and then run on several different systems. Like, you might like the fact that Travis is, I think, the only one that does the native strange architectures. You have to emulate it other places, which is a lot slower, 5 times slower or something.
Okay. Yeah. So kind of split that up, get the definition, and then create maybe multiple CI jobs.
Your CI scripts are really simple.
Yeah.
Very cool. The example script is just a few lines. It does not take much to do this. Comparing hundreds of lines it used to take.
Yeah, sure. And I didn't even scroll down here. You've got a nice grid on github.com/PyPA/CIBuildWheel that shows on GitHub Actions which is supported, on Azure Pipelines what's supported.
Oh, I was not right. Circle CI doesn't do Windows. AppFair does all three.
AppFair, Travis, Azure, and GitHub do.
Yeah. Travis does do macOS, but we can't test it.
Theoretically, it does. Gotcha. And then, I wonder about the M1, the Apple Silicon ARM versions versus the Intel versions. I don't know how well that's permeated into the world yet. But the fact they have Mac at all is kind of impressive.
Nobody has an M1 runner yet. There are a few places, I think, now that you can purchase time on one, but no runners. Last I checked, GitHub Actions, you couldn't even run it yourself on the M1. That may have changed. I don't know. That was a while back.
Yeah, I mean, there are some crazy places out there. I think there's one called Mac Mini Colo. I think that's what it's called. Let me see if that's I think that's it. Yeah. So you can go to these places like Mac Mini Colo and get a whole bunch of Mac Minis and put them into this crazy data center. But that's not the same as I upload a text file into GitHub that says run on Azure on GitHub Actions, and then that's the end of it, right? You probably got to set up your whole build system into a set of minis, and that doesn't sound very practical for most people.
Ideally, what you could do is, you just need one mini, and then you set up a GitHub Actions hosted runner, locally hosted runner. Yeah. And other systems do that too. GitLab CI was big on that. You can do anything on GitLab CI. We just haven't tested that because they don't have those publicly. But if you have your own, you can do that. I know somebody who does this basically with root and has a Mac Mini and runs the M1 builds on that.
Yeah.
But you could do that. I have a Mac Mini, and the lead developer of Cibuildwheel also has a Mac Mini with the M1. Well, he has an M1 of something. I don't know.
Sure.
Mine is a Mac Mini.
That's what I'm talking to you right now on. It's a fantastic little machine.
Yeah, it's very impressive. I love the way that boosts histogram. It was fast. I have a 16-inch almost maxed out MacBook, and the Mac Mini M1. It was faster on boost histogram than this thing.
Wow. Yeah, I have a maxed out 15 inch. It's a little bit older, a couple of years, but I just don't touch that thing unless I literally need it as a laptop because I want to be somewhere else. But yeah, I'm definitely not drawn to it. So you could probably set up one of these minis for $700 and then tie it up. But that's, again, not as easy as, just clicking the public free option that works. But still, it's within the realm of possibility.
Yeah, and Apple has actually helped out several, like I know Homebrew and a few others. They've helped out with by giving them either Mac Minis or something that they could build with. So they, I believe, Brew actually builds Homebrew actually builds on real M1s. I know it does because the builds are super fast. I remember that. Like it builds root in like 20 minutes. The root recipe. Like I maintain that. Yeah. And the normal one takes about an hour because it's running on multiple cores.
Right.
But it's like 3 times faster. It's done in like 20 minutes. I thought something was wrong when I first saw that.
It's it. How could it be done? Something broke. What broke? Interesting. All right, Henry, we're getting really short on time. We're a little bit over, but it's been a fun conversation. How about you give us a look at the future? Where are things going with all the stuff?
Next thing I'm interested in being involved with is scikit-build, which is a package that currently sort of augments setup tools, but hopefully will eventually sort of replace setup tools as the thing that you build with, and it will call out to CMake. So you basically write a CMake file, and this could wrap an existing package, or maybe you need some of the other things that CMake has, and this will then let you build that as a regular Python package. In fact, recently somebody sort of put together Cibuildwheel and scikit-build and the CMake example and built LLVM and pulled out just the Clang format tool and made wheels out of that. And now you can just do pip install Clang format. It's 1 to 2 megabytes. It works on all systems, including Apple Silicon and things. I just tried it on Apple Silicon yesterday. And it's a pip install. Now you can Clang format C++ code. And that's just mind-blowing. You can add it to pre-commit. So pre-commit CI, it runs in 2. I mean, I'd been fighting for about a week to reduce the size of the Clang format recipe from 600 megabytes to just under the 250. That was the maximum for pre-commit.ci. And then you can now pip install it under about a megabyte for Linux.
Oh, wow.
So that sort of thing. And I think that would be really, a really great thing to work on. It's been around since 2014, but it needs some serious work. And so I'm currently actually working on writing a grant to try to get funded to work on basically the scikit-build system, and looking for interesting science use cases that would be interested in adapting or switching an existing build system over, or adapting to it, or taking something that has never been available from Python and making it available. And yes, root might be one possible thing.
Scikit-build packages.
But I'm looking for a wide variety.
Yeah, how neat. Scikit-build package is fundamentally just the glue between setup tools, Python module, and CMake. Yeah, so it's a real way to take some of these things that were based on CMake and sort of expose them to Python.
Yeah, so you can just have a CMake package that does all the CMake things well, like finding different libraries, and that I'm a big CMake person. High-energy physics uses it very heavily. In fact, most C++ does. It's about 60%, I think, of all build systems are CMake based now. Going from get-where's numbers, but they make CMake. But I think it's very powerful. It can be used for things like that, and will really sort of open up a much easier C++, more natural in C++, and C and Fortran and things like that, and CUDA, than is currently available. Setup tools distutools is going away in Python 3.12. Setup tools is not really designed to build C++ packages or packages. It was really just a hack on top of distutools, which happened to build just Python itself.
Yeah.
So,
well, scikit-build sounds like the perfect tool to apply to the science space, because there's so many of these weird compiled things that are challenging to install and deploy and share and so on. So making that easier sounds good. All right. Well, I think we're probably going to need to leave it there just for the sake of time, but it's been awesome to talk about all the internals of supporting scikit-HEP, and people should check out Cibuildwheel. It looks like it, if you're maintaining a package either publicly or just for internal for your organization, it looks like it'll be a big help.
Yeah, if it's got any sort of binary build in it, yes.
Yeah, absolutely.
If not, build is fine.
Yeah, right. And I learned about build, which is good to know. All right. So before you get out of here, Henry, let me ask you the two final questions. If you're going to write some code, primarily Python code, what editor would you use?
Depends on how much. It'll either be VI if it's a very small amount. If it's a really large project that, let's say, takes several days, then I'll use PyCharm. And then I've really started using VS Code quite a bit, and that's sort of expanding to fill in all the middle ground and kind of eating in on both of the
Gotcha.
edges.
Yeah, there's some interesting stuff going there. Good choice. And
but all with the VI mode. Or
VI bindings, yeah, gotcha. And then notable PyPI package. I mean, we probably talked about 20 already. If you want to just give a shout out to one of those, that's fine. Or if you got a new idea.
I'm going to go with one that's unlike, might not get mentioned, but I'm really excited by it. The development of it is, I think the developer is quite new, but what he's actually done as far as the actual package has been nice. It needs some nice touches, but and that is plot text, PLOTTEXT. And I'm really excited about that because it makes the actual plots it makes are really, really nice, and they're plotted to the terminal, and it can integrate with Rich. And of course, I'm interested in it because I want to integrate it with I want to see it integrated with textual. I think a textual app that combines this with file browsers and things like that.
Yeah.
Could be incredible.
Yeah, so you could do things like with the terminal. Yes, yeah, so you could like cruise around your files, use your root IO integration, pull these things up here, and put the plot right on the screen, right? But in the terminal. Okay. Yeah, this is really cool. I had no idea. And this is based on Rich, you say?
It can integrate with Rich.
It integrates with Rich. Okay, got it. Yeah.
So as soon as I saw it, I started trying to make sure the two people were talking to each other, Will and the person who's developing this.
Yeah, exactly.
Please make these things work together.
That's very cool. They seem like they should, right? They're in the same general zone.
Yeah, cool. And they do now. There had to be some communication back and forth as far as what size the plots were and things. But right. This should work in it.
A good recommendation. Definitely one I had not learned about. So I'm sure people will enjoy that. All right, Henry, final call to action. People want to do more with wheels, Cibuildwheel, or maybe some of the other stuff we talked about. What do you tell them?
So we look through, I think one of the best places to go is the scikit-HEP developer pages, even if you have no interest in scikit-HEP tools or HEP at all. And that sort of shows you how all these things integrate together really well, and has nice documentation. Of course, Cibuildwheel itself is nice, and the PyPI, a lot of the PyPI projects have gotten good documentation, as well as packaging.python.org. We've updated that quite a bit to reflect some of these things. But I really like the scikit-HEP developer pages. I mean, I'm biased because I wrote most of them.
Nice. Yeah, I'll link to those, and I'll try to link to pretty much everything else that we spoke to as well, so people can check out the podcast player show notes to find all that stuff. I guess one final thing that we didn't call out that I think is worth pointing out is Cibuildwheel is under the PyPI, the Python Packaging Authority, so it gives it some officialness, I guess you should say.
Yes, that happened after I joined. One of the first things I wanted to do was I thought this should really be in the PyPI, and I started pushing for that, and the other developers were fine with that. And so we brought it up, and I actually joined the PyPI just before that by becoming a member of Build. So I got to vote on Cibuildwheel coming in, but it was a very enthusiastic vote, even without my vote.
Yeah, cool.
And PipX joined right at the same time too. So it was an exciting time.
Yeah, PipX is a great library. I really like the way PipX works. It's a great tool. All right, Henry, thank you for being here. It's been great. Thanks for all the insight on all these internals around building and installing Python packages.
Yeah. There's also a lot more on my blog. So isinumpy.gitlab.io. So that's also a good link to look. That links to all those other things, obviously, too.
Awesome. All right. Thanks again for being here. Yeah. See ya.
Thanks for having me.
Yeah, you bet.
It's fun.